Hi, and welcome to Trigonometric Applications and Models. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas, El Paso, and an assistant professor at Doña Ana Community College. This is for Pre-Calculus, Math 1508 at UTEP. Chapter 4, Trigonometry, comes to us from Larson's 10th edition Pre-Calculus text. Section 4.8, Trigonometric Applications and Models. Let's talk about solving some right triangles. When solving right triangles, whoa, sorry, didn't mean to do that. That was me, not you. When solving right triangles with angles A, B, and C, and we always use capital letters for the angles, we label the corresponding sides little a, it's across from angle A, little b across from angle B, and little c across from angle C, and we always make angle C the right angle, so side C is always the hypotenuse. And it works better with our whole Pythagorean a squared plus b squared equals c squared idea too. So we try to keep it similar. And so solving right triangles means we find all the values of the angles and we find the lengths of all three sides. So we're going to solve this triangle and round it 2 decimal places when necessary. I'm given that angle B is 54 degrees. And I'm given that side C is 15. Remember, side C is always going to be the hypotenuse across from the right angle. We don't need to solve for the right angle. It's going to be 90 degrees. So we really need to now find angle A, and side B. Okay, so from 54 degrees, I know that side B is opposite, and I have hypotenuse. That's the sine. The sine of 54 degrees will be B over 15. Multiply both sides by 15. Side length B will be the 15 times the sine of 54 degrees. Make sure your calculator's either in degree mode, or you could leave it in radian mode and make sure you use the degree symbol. And you'll get B equals 12.14. Always use the given information as much as possible. So when I try to find A, I'm going to go back to the reference of 54 degrees. I'm going to go back to the 15. Yes, if I have a value for B, I could use the Pythagorean theorem. But what if my answer for B is wrong? I'm guaranteed that my answer for A is wrong. So I use the given information as much as possible. From the 54 degrees, A is adjacent, so I'm going to use cosine. Cosine of 54 degrees is A over 15. Multiply both sides by 15. A is 15 cosine of 54 degrees, and in my calculator, that's 8.82. If you do not have a calculator in trigonometry, you will not fare well. Just get a calculator. Use your phone at home. There's a free Wabbit emulator for Android phones. Several free graphing calculators for iPhones. Just not the TI emulator that many of us are used to. Use it all you want. I don't care. You can go to my website at UTEP and you can get a free one because it's free on the Google Play Store. They put it on your computers. I think it works for Macs, but I'm not quite sure if the operating system works out. I'd have to check that and see. But make sure you bring a real calculator to exams. I know that I personally do not allow cell phones as calculators on exams, and I'm guessing many other instructors and professors across the country feel the same. Now, I found A and I found B. All that was left is I need to find angle A, but remember, all angles of a triangle must sum to 180 degrees. So I know angle A plus 54 degrees plus 90 degrees, the right angle, has to be 180, leaving me with A equals 36 degrees. I probably should have found that one first. It's the easiest, but I don't know. It's kind of nice to do all the hard work and let the easy part for last. Alright, this time I'm given A is 8.4 degrees and side little a is 40.5. Always work in reference to the given information. So this time I do the angle first. I know that 8.4 plus angle B plus 90 must be 180. Therefore, angle B is 81.6 degrees. Okay. Now, from the 8.4 that was given to us, I want to use opposite. And what do I want to solve for? Let's solve for B first, side B. So that's opposite and adjacent. I'm going to use tangent. The tangent of 8.4 degrees is 40.5 divided by B. Multiply both sides by B, and then divide by the tangent of 8.4 degrees. 40.5 divided by the tangent of 8.4 is 274.27. That's side length. Obviously, my triangle's not drawn to scale. You just need a basic idea. It doesn't have to be accurate. It has to be able to help you with setting up these equations. Again, in reference to 8.4, I have opposite. Now I want to find side C. I'm always using the given information and nothing that I've found, just in case. I don't want to compound my errors. So from 8.4, opposite and hypotenuse, that's going to be the sine. The sine of 8.4 degrees is 40.5 over C. Multiply both sides by C and divide by the sine of 8.4. I forgot my degree symbol. That's pure laziness on my part. When I divide, 277.24 is the side length C. Here's a couple of things you can check. First of all, the smallest angle, A, should have the smallest side length, 40.5, definitely the smallest. Also, the hypotenuse will always have the largest side length, and it is the largest side length. So these are reasonable. Can I guarantee them? No. But if I take 40.5 and I square it and I add to that 274.27 squared, and I'll find that it's super close to 277.24 squared when I add those. And due to rounding, it might not be exact, but close enough's good enough. What if I only have side lengths? Here I'm given side A is 25, the hypotenuse is 35. It's a right triangle, so I have two sides. I'm going to find my third side using the Pythagorean theorem. Pythagorean theorem tells me that my side B is about 24.49. Alright. What if I want to find angle A? With the given information, I have opposite and hypotenuse. So the sine of A is 25 over 35. But we know inverse trig functions now, so we can solve for the angle A by taking the inverse sine or the arc sine of both sides. The arc sine of 25 over 35. Make sure your calculator is in degree mode, or else you will get an answer in radians and your answer will be incorrect. In degree mode, 45.58 degrees. Now if I want to find angle B, I'm looking at adjacent and hypotenuse, so I'll use the cosine. Angle B is the arc cosine of 25 over 35, which is 44.42. Let's see. Side B and side A, super close to the same value. Angle A, side A a little longer, yes. So angle A, a little wider. But they're super close to being the same angle, super close to being the same lengths. These are probably very good answers. Alright, let's get into some artistry here. The sun is 20 degrees above the horizon. We want to find the length of a shadow cast by a part of a statue that is 12 feet tall. Now, here's my statue. I don't know, a blade raised in glory, I suppose. The sun's always in the corner. Ask any 4-year-old, they'll tell you the sun goes in the corner of your drawing. Sun rays come down, the shadow. From our shadow, the sun is 20 degrees above the horizon. Here's the horizontal, 20 degrees rise. I want to find the length of the shadow if the statue is 12 feet tall, and that does include the pedestal I put him on here. So my triangle really is S I'm trying to find, 20 degrees that I'm given, and 12 feet also given. So, I don't know, I'm doing this little drawing partially for humor, but it comes down to, for 20 degrees, I have 12 over shadow. That's an S, not a 5. So opposite and adjacent, tangent of 20 degrees is 12 over shadow. Multiply both sides by shadow and then divide by tangent of 20 degrees. In my calculator, either use the degree symbol or make sure you're in degree mode, or both. I find that 12 divided by the tangent of 20 degrees is 32.9697, which rounds to 32.97 feet for the length of my shadow. A ladder 20 feet long leans against the side of a house. Find the height from the top of the ladder to the ground if the angle of elevation of the ladder is 80 degrees. Here's a little safety tip. Your ladder should never be at an angle larger than 80 degrees due to tipping. And you should probably make it a little less than 80. 70, 75 is better, but whatever. We'll go with 80. Safety here, people. My little brick house, I want to know how high up the wall I reach for a 20-foot ladder. I'm looking for height, that's opposite. I'm given the hypotenuse, that's 20. So opposite and hypotenuse in reference to my 80 degrees. That's the sine of 80 degrees is h over 20. Multiply both sides by 20. 20 times the sine of 80 degrees is h, so it reaches about 19.7 feet up the side of the house. A 20-foot ladder, this angle is misleading. You're almost straight up. Just be safe. A passenger in an airplane at an altitude of 10 kilometers sees two towns directly east of the plane. The angles of depression to the towns are 28 degrees and 55 degrees. I want to know how far apart are A and B. Alright, so angle of depression, if I'm looking out, depression, I look down. So from a horizontal, this angle is 28 and this angle is 55. Let's take it apart. Given our diagram, if I have an angle of depression to town A of 55 degrees, I know that this is 90 degrees. 90 minus 55, the complement is 35 degrees. I want to find side Y. In reference to the 35 degrees, I have opposite and adjacent, so I'm going to use tangent. The tangent of 35 degrees is y over 10. Multiply both sides by 10, round to two decimal places, I'll get a y value of 7. So y is 7. For my town B, right, the angle of depression was 28 degrees. The complement is 62 degrees, so my angle here is 62 degrees. My opposite is x plus y. My adjacent is 10, so my tangent of 62 degrees is x plus y over 10. Multiply both sides by 10. 10 times the tangent of 62 degrees equals x plus y. And 10 times the tangent of 62 degrees is 18.81. I know that y is 7, so I could subtract 7 from both sides, and my x value, the distance the towns are apart, is 11.81 kilometers. 11.81 kilometers. Let's talk about the accuracy with this person looking out the plane and seeing the angle of depression and measuring it spot on at 28 degrees. That's pretty impressive. That must be a mathematician in the plane. Alright, don't like to fly? Let's take a boat. A ship leaves port at noon and has a bearing of south 29 degrees west. So facing south, we rotate 29 degrees towards the west. So this angle is 29 degrees. This is south, this is west, obviously. And let me see, the ship sails at 20 knots. Let's see. How many nautical miles south and how many nautical miles west will the ship have traveled by 6 p.m.? It leaves at noon. 6 p.m. is 6 hours later. 6 hours at 20 knots is 120 nautical miles. 120 nautical miles is my hypotenuse. 120 nautical miles. So if I want to know west, from the 29, west is opposite, and I have the hypotenuse. So opposite and hypotenuse tell me I'm using sine. The sine of 29 degrees is west over 120. Multiply both sides by 120, and I've gone 58.18 nautical miles to the west. From the 29 degrees, if I want to find south, this is adjacent. I'm given hypotenuse. So the cosine of 29 degrees is adjacent south over hypotenuse 120. Multiply both sides by 120, and I find the south is 104.95 nautical miles. Fantastic. Let's see what the next part is. Now at 6 p.m., of course, the ship is going to change course to due west. So it was here. Now I want to go due west. And I want to find the ship's bearing and distance from the port of departure at 7 p.m. So 1 hour later, still traveling at 20 knots, I'm going to add 20 to this length. So I know my full length is 78.18. I know my south is 104.95. I can find my angle. My angle is opposite over adjacent. Tangent of theta equals 20 plus 58.18 over 104.95. I have to use found values for this. Using arctangent, right, to get the angle by itself, theta equals inverse tangent of 78.18 divided by 104.95, 36.7 degrees. But I want to know the ship's bearing. I don't want to know theta. I specifically want to know it in bearing. So I'm facing south. I rotate 36.7 degrees to the west. Here's what I just noticed. I didn't find the distance. So let's do that. All right, so once again, we have to use found values, but we can find this distance using the Pythagorean theorem. We know that our distance will be the square root, and it looks like the distance formula, but it's not. It's just Pythagorean theorem. The west, 78.18 squared, plus the south, 104.95 squared. That's a 9, not a 7, and that's a squared. It looks stupid. It's not a 4. But this distance, rounded to 2 decimal places, will be 130.87 nautical miles, originally from port. Yeah, I've been using these notes for many, many, many years, and I just noticed that I never answered the distance. Guess it's a good thing I'm doing these videos. There you go, 130.87 nautical miles from port, not nanometers, just saying. Nautical miles from port, and that's Trig applications and models. Thank you for listening.